So I am setting a firm exam 1 date here right now. I told you at the first day of class that I was leaning toward this date. And that's going to be Wednesday, not next week, but the week after. Wednesday, that would be February 28th. Okay, it'll cover, for sure, chapters 0 through 5 fully, and possibly part of chapter 6. Possibly part of chapter 6. Okay. Today we're going to mostly focus on chapter 4. We'll start chapter 5 next week. We'll continue with chapter 4 next Monday as well, as starting chapter 5. And I think by next Friday, 1 week from today, we should be able to talk a little bit about chapter 6. Actually, I've been hinting at things in chapter 6 already. So some of the basic concepts probably would be something that we can get to before the exam. What are we like in this class? I claim we're like mathematical taxonomists. What do taxonomists do? Well, they study, classify things in nature, whether it be plants or animals. I can't exactly tell what she's looking at here, whether that's some sort of leaf or if that's some sort of like stick insect or something. I can't quite tell, but the taxonomists try to classify and understand the animal and plant world. Here's a picture related to this theory. It's called a subgroup lattice. Well, maybe if we have time, start talking about subgroup lattices a little bit today. Kind of a complicated looking one. It's related to a group called S4, which is something called a permutation group. And it's the subject of chapter 5, which we will again start next Monday. Okay, so we want to view groups and understand them and classify them and that kind of thing. Here's our main goals. To observe. And that's actually going to be the main thing that we do today. We're going to make calculations and observations about cyclic groups. To describe what we see, like a scientist would. To understand. I claim we can understand math better than a scientist can understand the world. The world is full of really, really deep mysteries. It's, you think about any area of science, it's hard to completely understand what's going on. There are mathematical models, for example, for atoms. But to really understand what's going on, you have to develop these theories, and the theories describe what we observe, but they don't really necessarily help you fully understand. I think in math, you can get further. You can pretty much completely understand certain things at least. To define and classify, and then something different than they do in science, to demonstrate, to prove. Scientific theories are never really fully proven. We just have stronger and stronger evidence for them. Theoretically, they could be falsified. Newton's laws were thought of as being fully valid as of 120 years ago, but then they had to get updated because of new discoveries. Einstein's discoveries and also quantum mechanics. But in math, we can use our deductive logic skills to try to prove things. I also try to, I hope you've noticed, revisit some concepts from time to time. And we can revisit, for example, the idea of an equivalence relation. That's a good thing to do from time to time. We will need them later. Did you know that you've dealt with equivalence relations since 4th grade? You have. How? I don't remember my 4th grade teacher talking about equivalence relations. Well, maybe if your 4th grade teacher was really advanced, they might talk about congruence of geometric objects, right? Of course, I can't draw perfectly, but we could pretend these two triangles that I'm drawing are congruent. What does that really mean? It means you can do some sort of rigid geometric transformation to move one triangle to be exactly on top of the other, consisting of a translation, rotation, maybe a reflection. That would be what it means to be congruent. And congruence of geometric objects is an equivalence relation. So even if your fourth grade teacher never said that, maybe they implicitly assumed, maybe they showed you these kinds of pictures and actually had physical manipulatives to actually do translations and rotations and reflections. But here's another way equivalence relations came up in fourth grade. Well, the following equation is a bit of a mathematical fib. I wrote this equation down, I think, the first day of class, but it's a bit of a fib. Thinking of the rationals as being the set of all fractions, a over b, where a and b are integers and b is non-zero, that's actually a bit of a fib. Huh? How could it be a fib? Doesn't that seem right? Well, the problem with it is that if you think of it purely in terms of symbols, that symbol, 1 over 2, is different than this symbol, 2 over 4. Is different than 3 over 6, is different than negative 4 over negative 8. But as rational numbers, we think of those as all being the same. They all represent the same rational number. So how do you deal with this fib? Well, it's equivalence relation. In truth, if you want the full truth, the elements of the rationals are actually equivalence classes of symbols like this under some equivalence relation. What is the equivalence relation? We could write a over b tilde c over d, or if we really wanted to, we could write an equal sign there instead. If and only if, when you cross multiply, you get the same thing. AD equals BC. We should really do a quick verification, not a full proof, that that's an equivalence relation. Is A over B equivalent to itself? Is the reflexive property true? That would be equivalent to saying A times B is A times B. Yes, that's true. If A over B is equivalent to C over D, does that go the other way around? Is it symmetric? This would imply A times D equals B times C. But that would imply what? Let's see, it would be C times B equals D times A, which would be the form of the product. Of course, multiplication of integers is commutative anyway, but would be the form of the product to say that C over D is equivalent to A over D. Yes, and multiplication of integers we can assume here is commutative. We're assuming we know everything there is to know about integers here. So the symmetric property holds. How about the transitive property? If A over B is equivalent to C over D, and C over D is equivalent to E over F, that's not the number E, it's also not an identity, just a symbol for an integer. That will imply AD equals BC and CF equals E, let me write it as DE. Just cross-multiplying effectively. Putting those equations together, essentially multiplying both equations, is going to imply ADCF equals BCDE. Is there a cancellation law for integers? Well, careful. The integers are a group under addition, not multiplication. However, you can multiply integers. And the integers do form what we will see is called a ring in a month or a month and a half or so. And it's a special kind of ring called an integral domain. In which the cancellation law under multiplication does hold. And it's commutative, so we can cancel anywhere we want here. The C's cancel and the D's cancel. AF equals BE, which would then imply A over B is equivalent to over F. Okay? So, in reality, this is a bit of a fib. In reality, each rational number is really an equivalence class of symbols like this. You have to then define what it means to add and multiply rational numbers, of course, then. But as far as what they actually are as mathematical entities, that's what they really are, is they are equivalence classes. And these different things like 1/2 and 2/4, those would be two different representatives of the same equivalence class, representing the number we think of as being, in lowest terms, 1/2. 0.5 as a decimal. Before we go on to talking more about cyclic groups, I should bring up one more important kind of subgroup that is in the book. Let G be an abelian group, and suppose you've got two subgroups, H and K. You can define what's called the product of those two subgroups. You can somehow multiply the subgroups. That's a bit strange. Denoted by HK, defined to be the set of all products of elements from H and K. So H and K are subgroups of G. G is an abelian group. This symbol, it's called the product of H and K, is a set. Initially, it's the set of all products of elements, little h times little k, where little h is in capital H and little k is in capital K. I claim this is a subgroup of G. Is that difficult to prove? It's not too bad. Let's try it with the two-step subgroup test. But again, in all these subgroup tests, you should first verify that the set is non-empty. Is HK non-empty? Yeah, because it's got the identity. That's typically the main thing you verify is in the set to verify it's non-empty, because E, the identity, is in H and it's also in K because they're subgroups of G. E is in H and E is in K. Well, I should say, write this. H is a subgroup of G and K is a subgroup of G. Those two facts imply that. But E is E times E. That's got to be in HK then, because the product of something in H times something in K. Putting the dot there, but I didn't have to. Let A and B be in the product of capital H and capital K. Is it closed? Is their product AB also in this product HK? You have to tease out what this means. What does it mean for A and B to be in this set? It means they are products like this. So you could maybe write A equals H1 K1 and B equals H2 K2 for some H1 H2 in capital H and K1 K2 in capital K. So their product cannot be written in this form. Can the product A times B be written as something in H times something in K? And the answer is yes, but you do need the fact that G is abelian to help you finish it. This plus the fact that G is abelian, these two things together imply AB equals H1 K1 equals times H2 K2, rearranged by the fact that it's abelian, to H1 H2. I'll put parentheses in here for emphasis, times K1 K2. That's in H since H is a subgroup of G, and this is in K since K is a subgroup of G. have those facts as well. And finally, given any element in this is its inverse also in this set. Two-step subgroup test. Let A be an HK. I could use the same symbols I did over there, H1 and K1. Let me just sort of rewrite it though. Then, since G is abelian, you could also fit the sock shoes property in here. By the way, from now on, you don't have to say the sock shoes property, you can just use it. I mean, it's kind of fun to say, so you may want to say it. The inverse of A is the inverse of H times K. By the sock shoes property, that's K inverse H inverse. And then since G is abelian, that's H inverse K inverse. And actually, it's okay if you want to just jump from here to here. You can say that's okay to do because G is abelian. Right away, you don't have to do the sock shoes property in between. Of course, in general, you have to use the sock shoes property if you're not assuming your group is abelian. But if you are assuming it's abelian, I'm okay with you just jumping from there to there. And once again, this is something in H, this is something in K, and so you're done. This is in HK. I guess I forgot to emphasize that over here, but that means this is in HK. Okay. What about if G is not abelian? Well, you need some extra conditions on H and K to guarantee this. It is sometimes still a subgroup, even when G is not abelian. But there are extra assumptions you need to make about H and K to make that true. And we'll see what those assumptions are in chapter 9. Chapter 9. Maybe I should look at it. Actually, it could be chapter 8. Chapter 8 or chapter 9. All right, we're on to our main topic for the day. And that is taking an empirical approach to cyclic groups. I think we should get really good at thinking about cyclic groups intuitively today before we look at the proofs of the theorems, at least some of those proofs next Monday. Now you've read that, hopefully, and so maybe you have these theorems somewhat in the back of your mind as I'm going to go through these examples. But they're easy to forget, so it never hurts to think about examples, gather data, essentially, about it. Oh, I did want to say one more thing, one more slide before we do that. This does include some things about cyclic groups. Before we get into cyclic groups, here are some basic facts that are worth emphasizing. I've already said this before. Zn is never a subgroup of Zm when m and n are different. Even though if m is bigger than n, Zn is a subset of Zm, it's not a subgroup. The operations are different. Un is never a subgroup of um when m and n are different. Once again, the operations are different. Also, un is not always a subset of um either. However, careful, Dn is, for example, a subgroup of D2n. Well, at least when you make their locations and orientations consistent. What do I mean? Suppose you got an equilateral triangle, and for a little extra emphasis, maybe sitting inside a circle. D3 is the dihedral group of order 6, 2 times 3. It's got 6 elements, 3 rotations, and although one of the rotations is the identity, and 3 reflections. If you're careful, you can consider those elements, which are really just functions. Remember, the elements of the dihedral groups are functions, transformations of the plane. So if you're careful, the same rotations and reflections that you have with D3 as functions can work for D6, for symmetries of a regular hexagon, as long as you're careful. One way you could make the hexagon is you could find, well, so you say the center is right there. You could find the intersection of these lines of symmetry with that circle and make those also vertices of your regular hexagon. Like this. This is not a great drawing, but you get the idea. Pretty bad drawing for that hexagon, especially. Okay. You get the idea. It's going to have the same rotational symmetries plus more rotational symmetries. And it's going to have the same reflectional symmetries plus more. The original reflectional symmetries, this across this line, and this line, will also be reflectional symmetries for the hexagon. Ignore how badly drawn it is. Okay. So, yeah, it's the same elements, same functions, same operation, function composition. And Dn is a subset of D2n, at least when you put the objects in a consistent way. It's also worth emphasizing that every cyclic group is abelian. And that's because of what cyclic groups are. G is a cyclic group if it has a generator, if there's an A, so that this is true. All elements of G are powers of A. Integer powers of A. You got 2 arbitrary integer powers of A. They will commute. Because addition of integers is commutative, that's the reason, plus the rules of exponents. So every cyclic group is abelian, and therefore, it's also true for the same reason that every non-abelian group is non-cyclic. So if you're ever asked to come up with a non-cyclic group, quickest thing to do is write down a non-abelian group like D3 or D4. And it can't be cyclic. Right? Does that make sense? These two implications are contrapositives of each other. They mean the same thing. And since this one is true, this one must be true. This is P implies Q. This is not Q implies not P. Remember truth tables from discrete? Did you do those? These mean the same thing. They're equivalent. All right, now let's get into the cyclic groups, taking our empirical approach here. Here's some questions you can ask about cyclic groups. Technically, the empirical observations are not really on this slide. We're going to do the empirical observations together on the board. If you know the order of a cyclic group, is the number of generators completely determined? For example, we saw that Z6 has generators. Do you remember? Figure it out in your head? I wrote it down on the board last time. Z6 has generators
1 and 5.
1 and 5, 2 generators. Does every cyclic group of order 6 just have 2 generators? I hope you have the intuitive feel that yes, that's true. Can we find the generators? Yes, you can do that too. In a general cyclic group of order 6, here is the cyclic group of order 6. It's got 2 generators, A and A to the 5th just like 1 and 5 are generators of Z6. And that kind of property is going to hold for all cyclic groups, including infinite cyclic groups too. The only generator of Z, there are only two generators of Z, plus or minus 1. Nothing else is a generator of Z. Can we determine whether two powers of a generator result in equal elements or no? The answer is yes. We'll consider examples here in a few minutes. If you have a generator, A, can we determine the orders of its powers? Like what's the order of A squared, or the order of A cubed, or the order of A to the 4th? We know the order in this example here of A itself is 6, and also the order of A to the 5th must be 6, since it generates the whole group. If you want to double check that, A to the 5th to the first power is A to the 5th. A to the 5th to the second power is A to the 10th, which is the same as what? In the cyclic group of order 6. A to the 4th. A to the 5th cubed is A to the 15th, which in the cyclic group of order 6 is A cubed. 15 mod 6 is 3. A to the 5th to the 4th is A to the 20th. Mod the power of the exponent by 6, you're going to get A squared. A to the 5th to the 5th is A to the 25th. Mod by 6, that'll be A to the 1st. And A to the 5th to the 6th is A to the 30th. Mod by 6, you get 0. A to the 0 is E. So yeah, A to the 5th is a generator. It also has order 6. It's also going to be true that the order of an element is the same as the order of the cyclic subgroup it generates. This shows that. The order of A to the 5th is the same as the order of the cyclic group it generates. In this example, that's 6. We can ask, how do the orders of the elements of a cyclic group relate to the order of the group itself? This is a little bit trickier, perhaps. Do you think you have an answer to this based on your experience so far? Or maybe based on reading and remembering what you read? G is a cyclic group. It's got a generator A, and other elements that are powers of A. How do the orders of all those elements relate to the order of the entire group? Go to this example again. The order of the identity is 1, always. The order of A is 6. The order of A to the 5th is 6. The order of A squared is what? Square A squared, get A to the 4th. Cube A squared, you'll get A to the 6th, which is E. So the order of A squared is what? 3. The order of A cubed is 2. A cubed squared is A to the 6th is E. The order of A to the 4th, well, what's the order of the cyclic subgroup it generates? Squared, get A to the 8th, which is A squared. Cube it, get A to the 12th, which is back to E. The order of A to the 4th is 3. So orders are 1, 6, 3, 2, 3, 6. 1, 6, 3, 2, 3, 6. And the order of the whole group is 6. How do those orders of those elements related to 6?
6 is divisible by each of them?
Yeah, 6 is divisible by each of them. This is a 2 here. They all divide 6. What types of subgroups do cyclic groups have? Can they have non-cyclic subgroups? No, they can't, actually. Every subgroup of a cyclic group must be cyclic. And in fact, for each number, each integer, positive integer that divides the order of the group, the cyclic group, there's exactly one cyclic subgroup of that order. 3 divides 6. There is one cyclic subgroup in this example of order 6. It's this one right here. 2 divides 6. There's one cyclic subgroup of order 2. The one generated by A cubed. All right, let's get a little bit more precise and continue more observations. Or are we at quiz time? Almost to quiz time. Let's do another example. We'll consider relatively small orders here before the quiz. We only have time for one more example. After quiz, we'll do bigger groups. Suppose A has order 5. So the cyclic subgroup generated by A would be A squared, A cubed, A to the 4th. 5 is prime. The orders of subgroups of cyclic groups must divide the order of the whole group. The only divisors of 5 are 1 and 5. E does generate just itself. The order of E is 1, but every other element generates the whole group. Got to mod the powers by 5 here. Those are the powers of A squared. Gives you the whole group. Powers of A cubed. Again, mod by 5. A cubed to the squared is A to the 6th. Mod by 5, get A to the 1st. A cubed cubed is A to the 9th. Mod by 5, get 4, A to the 4th. A cubed to the 4th is A to the 12th. Mod by 5, get A squared. And A cubed to the 5th is A to the 15th. Mod by 5, get 0. A to the 0 is E. This generates the whole group too. As does A to the 4th, as you can check. So this one has 4 generators. And the subgroups only have order 1 and 5. They're the trivial subgroup and the group itself. There are no non-trivial proper subgroups to this group. Okay, let's take the quiz.